Lecture 2.1, Day 2, Step Functions and More Sandwich Theorem. This is the miraculous staircase in the Loreto Chapel in Santa Fe, New Mexico. It makes two 360-degree turns without support. It's considered miraculous because at the time it was built, a staircase was needed to the choir loft so that the girls in this girls' school could get to the choir loft without having to climb a ladder in their long dresses. No one thought a staircase could be built, but an itinerant carpenter came along with his tools on his donkey and built the staircase and left without charging. Now it's only used for brides and grooms to pose for wedding photos in what is now a private chapel. Step functions are sometimes used to describe real-life situations. Our book refers to one such function, y equals integer x. This is the greatest integer function. The TI-89 contains the command intx, but it is important that you understand the function rather than just entering it in your calculator. The greatest integer function, y equals the greatest integer that is less than or equal to x. If we make a table and start with x equals 0, the greatest integer that is less than or equal to 0 is 0. So we put a dot on the graph. If we move over a little bit to the right, the greatest integer that's less than or equal to 0.5 is still 0. If we move to 0.75, the greatest integer that's less than or equal to 0.75 is still 0. But if we let x equal 1, 1 is an integer. So the greatest integer that's less than or equal to 1 is 1. And we have a jump or a step. We could continue picking points until we filled in the line segment. And it would look like this, with a solid dot at the left and an open circle at the right. Now, if we try x equals 1.5, the greatest integer that is less than or equal to 1.5 is 1. And we continue this pattern. At 2, we get another step, because the greatest integer that's less than or equal to 2 is 2. Graph, it looks like this, which kind of reminds us of a staircase. The greatest integer function is also called the floor function. The notation for the floor function looks like this. So we have a special symbol that we use for floor function. This notation was introduced in 1962 by Kenneth E. Iverson. 1962, which is quite recent by mathematics standards. Some books use other symbols for the greatest integer function. We will not use these notations. The TI-nspire command for the floor function is either integer x or floor x. Graph the floor function. Use zoom standard. We use f1x equals floor x. And you can find the floor command by pressing the catalog key and then F, and then selecting floor. And here's our graph. Notice that the calculator does not include the open and closed circles at the endpoints. It probably knows there should be open and closed circles, but it just does not have the resolution. The least integer function is y equals the least integer, that is greater than or equal to x. Once again, we make a table. If we start with 0, the least integer that's greater than or equal to 0 is 0. And if we move to the right and let x equal 0.5, the least integer that's greater than or equal to 0.5 can't be 0 because 0 is not greater than 0.5. It has to be 1. If x is 0.75, the least integer is still 1. If x is 1, the least integer is still 1. And we can connect the dots. Notice that this time the open circle is on the left-hand side and the closed circle is on the right-hand side. Now if we try 1.5, the least integer that's greater than or equal to 1.5 is 2. But at 2 is an integer. It's still 2. We don't get a jump until we go just past 2. In the entire graph, it looks like this. Easy to confuse with the greatest integer function. Both functions start with a dot on the origin, but the first line segment on the greatest integer function goes to the right, is greater. The first line segment on the least integer function goes to the left. The least integer function is also called the ceiling function. The notation for the ceiling function is y equals ceiling function x. The TI-nspire command for the ceiling function is ceiling x. Don't worry, there are not wall functions, front door functions, fireplace functions, or any other building parts, only floor and ceiling functions. Now we're going to shift gears for the second half of the lecture. We're going to use the sandwich theorem to find the limit as x goes to 0 of sine x over x. If we graph y equals sine x over x, it appears that the limit as x approaches 0 of sine x over x equals 1. Now we saw this in our last lecture. We were pretty well convinced that the limit was 1, but it's not a proof. What we want is a proof. We might try to prove this using the sandwich theorem as follows. Sine x is greater than or equal to -1, and sine x is less than or equal to 1. So we could try taking the limit as x goes to 0 of -1 over x, which is less than or equal to the limit as x goes to 0 of sine x over x, which is less than or equal to the limit as x goes to 0 of 1 over x. We've got a problem though. Neither one of these new limits are defined since the left and right-hand limits do not match. You can look at the graph of 1 over x to see that. We will have to be more creative. Just see if you can follow this proof. Don't worry that you wouldn't have thought of it yourself. Confidentially, neither did I. Note, the following proof assumes positive values of theta. You could do a similar proof for negative values. So we start with a unit circle, and we have a point xy on the circle. We draw a right triangle, so we have an angle theta and a radius of 1. So the horizontal distance is cosine theta. The vertical distance is sine theta. Now we'll draw a second triangle by extending the radius to a point directly over 1, 0. And we'll call that triangle AOT. AT, which is this side, divided by 1, which is this side, would be opposite over adjacent, so that's equal to tangent theta. So we can just say AT equals tangent theta. So the coordinate of t is 1 tangent theta. Now, we draw a line segment between point P and A, and we can see by looking that the area of triangle AOP is less than or equal to the area of the sector AOP. There's the sector AOP, and that is less than or equal to the area of triangle OAT, which is the large triangle. So this might already give you a hint that we're looking at the sandwich theorem. The area of triangle AOP is 1/2 times base times height, or 1/2 times 1 times sine theta. The area of sector AOP is theta over 2 pi times pi r squared. Theta over 2 pi is that portion of the circle that we're using. And remember, r is 1, so r squared is just 1. So we can simplify to theta over 2. The area of triangle OAT is 1/2 base times height, or 1/2 times 1 times tangent theta. And you can see now that we're leading into the sandwich theorem. Multiplying through by 2, we have sine theta is less than or equal to theta, which is less than or equal to tangent theta. Or sine theta is less than or equal to theta, which is less than or equal to sine theta over cosine theta. Now, if we divide by sine theta, we get 1 is less than or equal to theta over sine theta, which is less than or equal to 1 over cosine theta. And we take the reciprocals. When we do that, that reverses the inequalities. So we now have 1 is greater than or equal to sine theta over theta, which is greater than or equal to cosine theta. And switching it end for end, we get cosine theta is less than or equal to sine theta over theta, which is less than or equal to 1. We're almost there. Now, if we take the limit in all three places, the limit as theta goes to 0 of cosine theta should be less than the limit as theta goes to 0 of sine theta over theta, which is less than or equal to the limit as theta goes to 0 of 1. The limit as theta goes to 0 of cosine theta is just 1. The limit as theta goes to 0 of 1 is 1, obviously. So, by the sandwich theorem, the limit as theta goes to 0 of sine theta over theta equals 1, which was what we surmised in the last lecture. Now we know for sure because we have the proof.